The moon is not quiet. I know it looks quiet. It has looked quiet every single night of your entire life. But on April 6th, 2026, 4 astronauts flew behind it and watched it get hit 5 times in 1 hour. 5 explosions on a world we treat like a postcard. NASA's telescopes catch about 20 of these a year. The Artemis II crew saw 5 in 60 minutes, so either the moon had a really bad day, or we have been watching it from the wrong place for 400 years, and here is where it gets serious. A new study estimates that a lunar base the size of the ISS would be struck by up to 23,000 micrometeoroids every single year. 23,000. That is not a threat. That is a weather system. A permanent, invisible, unstoppable storm that never pauses, never moves on. And we want to build there. Not just visit. Build. Permanent outposts. People living and working on that surface for months, then years, then permanently. So the question is no longer whether the moon is dangerous. The Artemis II crew answered that in 60 minutes. The question is whether we truly understand what we're building into, and whether our plans are anywhere near ready for the reality of it. If you are new here, welcome to Interstellar Dreams, subscribe, and get comfortable. Because by the end of this, the moon will never look the same to you again. Now, settle in and let's ease into it. Part 1. The Flashes in the Dark. On April 6th, 2026, 4 human beings flew behind the moon and watched it get hit. Not once, not twice. At least 5 times in a single hour. Bright, sharp flashes of light punching into the lunar surface while the crew of Artemis II drifted through the most extreme viewing geometry any person has ever occupied. Meteoroids, some no bigger than a walnut, slamming into rock at tens of thousands of miles per hour, each one detonating with the energy of several kilotons of TNT. And here is the part that should bother you. NASA's ground-based monitoring program, the one that has been watching the moon with telescopes since 2006, averages about 20 detectable impacts per year. 20 in 12 months. The Artemis II crew saw 5 or 6 in 60 minutes. So either the moon suddenly got a lot more dangerous on that particular Sunday in April, or we've been staring at it from the wrong place this entire time. This is not a story about a new threat. It is a story about a blind spot, one that has been sitting between us and the moon for as long as we have been watching. And what Artemis II actually did, without anyone planning for it, was rip that blind spot wide open. Before we get into it, if you are new here, and this is the kind of thing that keeps you up at night in the best way, hit subscribe so you do not miss what comes next. And I will say this up front, by the time we are done here, every time you look up at the moon, you are going to remember what is actually happening to its surface right now, in the dark, where nobody's watching. That changes things. Now settle in, because this one builds slow and hits hard. Let me take you inside that moment. The Artemis II mission was never designed to be a lunar science observatory. It was a shakedown cruise. The whole point was to prove the hardware worked before you trusted it with something bigger. 4 astronauts, Commander Reed Wiseman, pilot Victor Glover, mission specialists Christina Koch and Jeremy Hansen, strapped into the Orion capsule on top of the Space Launch System, the most powerful rocket NASA has ever built. The mission profile was a free return trajectory, a big sweeping loop around the moon that would carry the crew farther from Earth than any human being has travelled since Apollo 17 in 1972. More than 50 years between trips. More than half a century since anyone had seen the moon from that close with their own eyes. And the objectives for this flight were entirely about the vehicle. Test the spacecraft systems under real deep space conditions. Validate the life support across the full mission duration. Confirm that navigation and communication held together on the far side, where the moon blocks every signal from Earth. Prove that Orion could keep 4 people alive and functional for the full 10-day mission envelope. Nobody put count meteor impacts on the flight plan. Nobody scheduled an observation window for surface bombardment events. That was not what this trip was for. But space has a way of handing you data you did not ask for. And sometimes the data you did not ask for turns out to be the most important thing you bring home. As Orion swung around the far side of the moon on April 6th, the spacecraft entered a geometry that no human crew had ever experienced. Not during Apollo, not during any mission in the history of spaceflight. The moon slid directly between Orion and the Sun, and because of the precise orbital timing, because of where the Earth and Moon and Sun happened to be arranged on that particular day, something extraordinary happened. The moon did not just block the Sun from the crew's perspective, it created a total solar eclipse, observed not from Earth's surface the way we normally see them, but from behind the moon itself. Think about that for a second. Every total solar eclipse you have ever seen footage of, every one that has ever made the news, was watched by people standing on Earth while the moon's shadow passed over them. This was the opposite. The crew was sitting in the moon's own shadow, looking back toward the Sun, watching the solar corona flare out around the black lunar disk from the other side. From space. From behind the thing doing the blocking. Reed Wiseman would later describe it in language that did not sound like a test pilot. And test pilots are not typically known for their poetic vocabulary. He called the experience transcendent. He said the corona extended outward for what appeared to be 10 solar diameters, a halo of superheated plasma stretching far beyond the edge of the lunar silhouette, visible in a way that no Earth-based eclipse can replicate because there was no atmosphere between the crew and the light, no air molecules scattering photons, no humidity blurring the edges, no thin veil of sky between the observer and the phenomenon, just vacuum and light, and the black circle of a world that has been orbiting us since before anything on Earth was alive to look up at it. And while that corona blazed in silence around the rim of the moon, something else caught their attention on the dark face below them. Flashes, short, sharp bursts of light against the unlit surface. Not reflections from spacecraft hardware, not instrument artifacts or sensor glitches, impacts, real, physical, violent impacts. Wiseman reported at least 5 distinct events during roughly a 1-hour observation window. 5 explosions on a world we think of as dead. 5 bursts of light on a surface we treat like a museum exhibit. Something frozen, something preserved, something that stopped changing a long time ago. Now, here is where your brain is going to want to do something very natural and very wrong. It is going to want to treat this as a discovery. As if the crew stumbled onto something new happening on the moon, as if April 6th was special, as if the moon woke up, as if some unusual event made it suddenly more active than normal. They did not discover that. What they found was something old happening on the moon, something ancient, something constant, that we have been systematically unable to see from where we sit. And I need you to understand why that distinction matters more than the flashes themselves. Because if this were a new phenomenon, it would be a curiosity, an interesting data point to file away. But if this is an old phenomenon that we have been missing, then everything we thought we knew about the rate and frequency of lunar impacts needs to be reconsidered, and so does every engineering calculation built on top of those numbers. Think about the geometry for a second. Orion was roughly 4,000 to 7,000 miles above the lunar surface during this passage. That is close. Drastically, almost absurdly close compared to where we normally observe the moon from, which is about 239,000 miles away, sitting at the bottom of 100 kilometers of turbulent, light-scattering, signal-smearing atmosphere. The crew had no atmosphere between their eyes and the surface, no light pollution bleeding in from nearby cities, no turbulence distorting the image, no convection cells in warm air bending the light path on its way to the detector. And the sun was gone, blocked entirely by the moon itself, which meant the near-side surface was as dark as it ever gets, illuminated only by the soft reflected glow of Earthshine. Sunlight bouncing off our planet, crossing 239,000 miles of vacuum and falling gently across the lunar terrain like a faint blue-grey wash. Enough light to reveal surface features, not enough to drown out a flash. Christina Koch captured photographs of the lunar limb, the edge of the moon's silhouette, with craters and ridgelines faintly visible against the solar corona burning behind it. Jeremy Hansen described the coronal streamers extending outward in filaments and structures he had never seen in any simulation or training image. Formations that only become visible when you remove every layer of interference between the observer and the sun. The crew was not just seeing the moon differently, they were seeing light differently. They were occupying a vantage point that stripped away every filter human beings normally look through, and what remained was raw, unprocessed reality. This was not a designed experiment. Nobody at NASA sat down and said, "Let us put a crew in the perfect position to detect faint impact flashes on the lunar surface." It was an accident of observation, a coincidence of orbital mechanics and mission timing. But it created the most perfect natural impact detection laboratory that has ever existed. Maximum contrast between flash and background. Minimum interference from atmosphere or scattered light. Zero atmospheric distortion in the optical path. A dark surface lit only by faint Earthshine, monitored from close range by 4 sets of human eyes and multiple camera systems with nothing between them and the moon but vacuum. And in that window, in that brief, unrepeatable hour of perfect conditions, the moon revealed what it always does. It gets hit. Constantly. Relentlessly. Without pause and without mercy. The crew just happened to be in the one place where you could actually see it happen. And that is the thread you need to hold on to for everything that follows. The moon did not change. Our view of it did. Here is what makes the initial count so unsettling, and why I keep coming back to it. 5 to 6 impact flashes in approximately 1 hour. On its own, sitting in isolation, that number might not mean much. It could be a statistical fluke, it could be a lucky window, but place it against the only long-term dataset we have, the only sustained attempt to count these events from Earth, and it starts to feel less like a fluke and more like a crack in the foundation of what we thought we understood. NASA's Automated Lunar and Meteor Observatory Program, known as ALAMO, has been logging confirmed lunar impact flashes since 2006. That is nearly 2 decades of patient systematic observation. Over that time, the program detects on the order of 20 impacts per year. Some years a few more, some years a few fewer, but the long-term average sits comfortably in that range, 20 per year. That is roughly 1 confirmed flash every 18 days, 1 visible impact event every 2.5 weeks, on a world that presents its entire near side to our telescopes every single night. The Artemis II crew saw 5 or 6 in 60 minutes. Now, before you let that comparison run away with you, before the math starts spiralling, there are important caveats, and they matter. The ALAMO program observes from Earth through the atmosphere with 14-inch class telescopes, solid instruments, but not space-grade optics operating in vacuum. The program can only watch the moon during specific lunar phases, roughly 10 nights per month when the near-side dark regions are visible against the right lighting conditions. You need the dark part of the moon facing Earth, and you need it to be nighttime at the telescope site, and you need clear skies, and you need the moon at a reasonable elevation above the horizon. Stack all those constraints together, and the actual usable observation time shrinks dramatically. On top of that, the program is limited to detecting the brighter end of the flash spectrum. Faint events, the ones produced by smaller impactors that still hit with enormous energy, but do not produce enough light to be picked up from 250,000 miles away through an atmosphere, those get swallowed by noise. They vanish into the background. They were there, they happened, and nobody recorded them. So comparing the two numbers directly, 20 per year from Earth versus 5 per hour from orbit, is not quite a fair comparison. They are measuring different things under profoundly different conditions, but that is exactly the point. That is the whole point of this entire story. The mismatch does not mean the moon got busier on April 6th. It does not mean there was a sudden spike in meteoroid activity that just happened to coincide with the mission. It means our usual way of watching, the way we have been doing it for 20 years, has been filtering out most of what is happening, and Artemis II, without intending to, without anyone designing the mission for this purpose, dropped a crew into the one observational window where those filters disappeared entirely. What they saw was not an anomaly. It was a sample of the real rate, captured under conditions that have never existed before in the history of human observation. The question is not why they saw so many. The question, the one that should keep you watching, is why we've been seeing so few. Some of those flashes appeared clustered near the equatorial region. At least one was reported near the South Polar area, which is going to matter enormously later in this story when we talk about where humanity plans to build its first permanent lunar outpost. There was even a suggestion among analysts reviewing the data that the clustering might indicate a meteoroid stream, a coordinated ribbon of cometary debris that the moon passed through during that specific window, producing a short burst of elevated activity. That is plausible. Sporadic meteoroid streams are well documented, and they are known to produce temporary spikes in flux when the moon or Earth passes through them. But even if a stream explains why the impacts were clustered in space and time, it does not explain away the detection rate. Because the physics of those impacts, the brightness, the energy, the optical signature, all of that tells us these were not extraordinary events. They were ordinary events, typical of the background meteoroid environment, seen under extraordinary conditions that let the crew detect what ground-based systems never could. The crew's emotional reaction reinforces this interpretation. Wiseman did not sound alarmed. He did not radio Houston with urgency in his voice. He sounded amazed. The word giddy appeared in post-mission commentary. Unreal came up more than once. These were not people witnessing a crisis. They were people witnessing something beautiful and violent that they had never been told to expect. And that reaction, that genuine surprise, is itself a data point worth noting. It tells you that even the people trained to fly this mission, the people who spent years in simulators and briefing rooms preparing for every contingency, were not briefed to expect visible impacts at this rate. The institutional assumption going into the mission was the same as the public one. The moon is quiet. The moon is still. The moon just sits there and waits for us to visit. It does not. It never has. And while 5 flashes lit up the dark side of the moon in front of 4 astonished astronauts, most of the world was watching something else entirely. The NASA livestream during the Farside passage focused, understandably, on the visual spectacle. And what a spectacle it was. The first total solar eclipse ever observed from behind the moon. The corona blazing outward in structures and streamers that no ground-based eclipse could ever reveal with that level of clarity. Earthshine painting the near-side terrain in pale blue-grey tones that made the moon look like it was glowing from within. Christina Koch's camera capturing the lunar limbs silhouetted against the sun's outer atmosphere in images that will end up in textbooks for the next century. Jeremy Hansen describing the coronal prominences and streamer structures in real time with the controlled excitement of a pilot who has trained for years to remain measured in exactly this kind of moment. The coverage was beautiful. It was genuinely historic. And it almost completely buried the most important scientific observation of the entire flyby. Impact flashes were mentioned in the broadcast, yes. Wiseman's report was acknowledged by the commentary team. But in the context of everything else happening on screen, the flashes were treated as a sidebar. A cool bonus observation. A fun footnote. Something worth noting while the real story, the eclipse imagery, the coronal science, the sheer unprecedented visual drama of watching Earthshine illuminate the moon from lunar orbit, commanded the audience's attention and dominated the media cycle. And I want to be clear, that is not a criticism of NASA or the journalists covering the event. They covered what was visually overwhelming, and the eclipse was visually overwhelming. But it is a perfect, almost poetic illustration of the central problem that runs through this entire story. We are drawn to the beautiful. We are drawn to the photogenic. We are drawn to the thing that makes the best thumbnail, the best headline, the best 15-second clip. And sometimes the thing that actually matters, the thing with the deepest implications for human spaceflight and lunar settlement, and our understanding of the environment we are about to move into, is happening in the margins of the frame while everyone is looking at the main subject. The flashes were there. The data was real. 5 or 6 confirmed impacts, witnessed by human eyes for the first time in history from lunar orbit. But the information was buried inside an aesthetic moment so visually overwhelming that the scientific signal almost got lost in the noise of its own beauty. Important data, hiding in plain sight, overlooked not because it was classified or obscure, but because something prettier was happening at the same time. And if that pattern does not sound familiar, you have not been paying attention to how we have been watching the moon for the last 400 years. Because we have always preferred the beautiful version, the quiet version, the postcard version, and the moon has been getting pummeled the entire time. The real question is not what happened during the Artemis II flyby. The real question, the one this whole story is building toward, is what has been happening every single day, every single hour, on a surface we cannot properly monitor, in conditions we cannot replicate from Earth. And the answer to that question is going to change how you think about everything we are planning to build up there. Part 2, the moon as a shooting range. The reason those impact flashes surprised the Artemis II crew, and the reason they should surprise you, is that we have spent our entire lives looking at the moon and seeing something that is not there. Stillness. The moon looks frozen. It looks like a photograph of itself, hanging in the sky, unchanging from night to night, century to century. Every culture that has ever gazed upward has seen the same thing. A quiet companion, a silver disk, a world where nothing happens. We named its features after seas: Mare Tranquillitatis, Mare Serenitatis, the Sea of Tranquility, the Sea of Serenity. We looked at a blasted, airless, impact-scarred wasteland and called it serene. That tells you everything about the power of distance to deceive. That impression is a lie told by distance and atmosphere, and to understand why, you need to understand what is actually standing between you and the moon every time you look up at it. You're not looking at the moon, you're looking at the moon through a filter. A thick, turbulent, light-scattering filter 100 kilometers deep, composed of nitrogen and oxygen and water vapor and dust, and the accumulated photons of every city and streetlight on the night side of the planet. That filter does something to the signal. It blurs it. It dims it. It strips out the faint end of everything you're trying to see, and what remains, the crisp silver disk hanging above the horizon, is a processed version of reality, cleaned up and smoothed out by 100 kilometers of imperfect optics between your eye and the surface. You have never seen the moon. You have seen what the atmosphere allows you to see of the moon, and those are not the same thing. The moon has no atmospheric envelope. None. Not a trace of meaningful gas between its surface and the vacuum of space. The lunar atmosphere, if you can even call it that, is so thin it is technically classified as an exosphere, a region where gas molecules are so sparse that they almost never collide with each other. The total mass of the lunar exosphere is estimated at about 10 metric tons. Earth's atmosphere masses 5 quadrillion metric tons. The moon's gas envelope is, for all practical purposes, nothing. A ghost of an atmosphere, a rounding error. When something approaches the moon from space, there is no atmospheric layer to slow it down, heat it up, or break it apart before it arrives. There is no first line of defense. There is no line of defense at all. There is only surface. On Earth, when a grain of sand-sized meteoroid comes screaming in at 40 or 50 kilometers per second, it hits our atmosphere about 100 kilometers up and begins to compress the air in front of it so violently that both the air and the particle heat to thousands of degrees. That is what a shooting star is. It is not the rock burning in the intuitive sense, not like a log on a fire. It is the atmosphere being superheated by compression. The particle rams into increasingly dense air at a speed so far beyond anything our daily experience prepares us for that the physics becomes almost alien. The air in front of the meteoroid cannot get out of the way fast enough. It piles up, it compresses, and compressed gas heats up. The leading edge of the particle's path becomes a column of plasma, a streak of superheated, ionized gas that glows brilliantly across the spectrum, producing the white-hot streaks we see on clear nights from our backyards. And in the vast majority of cases, the particle never reaches the ground. It disintegrates, vaporizes, becomes a brief streak of light and a wisp of metallic gas 60 miles above your head, consumed entirely by the act of entering. Earth's atmosphere is a shield, not a perfect one, but an extraordinarily effective one. It filters out nearly everything below a certain size threshold, and it slows down much of what remains. We live, every day of our lives, under a planetary defense system we never think about, never appreciate, and have never had to do anything to maintain. The Moon has none of that. No filter, no brake, no buffer zone, no first contact, no compression heating, no plasma column, no atmospheric deceleration. A particle that would become a harmless shooting star on Earth would become a brief, pretty streak of light that interrupts a conversation and prompts someone to say, "Make a wish," hits the lunar surface at full cosmic velocity, unmodified, undimmed, exactly as fast as it was when it was drifting through interplanetary space before the Moon's gravity began pulling it in. We're talking 11 to 70 kilometers per second, depending on the particle's origin and approach angle. To put that in terms your brain can actually process, 70 kilometers per second is over 156,000 miles per hour. At that speed, you could cross the entire United States coast to coast in about a minute. You could circle Earth in less than 10 minutes. You could travel from here to the Moon in roughly 45 minutes, which is faster than most people's morning commute. And when something moving that fast hits solid rock, it does not bounce, it does not skip, it does not slow down gracefully over any meaningful distance. It stops in microseconds, a distance measured in millimeters, and all of that kinetic energy, every last joule of it, converts instantaneously into heat, pressure, and light. This is what an impact flash actually is. Not a gentle contact, not a collision in any sense the word usually carries. The meteoroid hits the surface and the point of contact becomes a plasma. The rock vaporizes, not melts, not cracks, vaporizes, going directly from solid to superheated gas in a time so short that the word instant does not capture it. The impactor vaporizes. The surrounding regolith at the point of contact vaporizes. A shockwave radiates outward into the regolith at speeds faster than sound travels in rock, which is itself several kilometers per second, and that shockwave excavates a crater, not over seconds but in milliseconds. The material excavated and ejected outward in a cone of debris that, on the Moon, flies ballistically in every direction with no air resistance to slow it down, no drag to limit its range, no atmosphere to burn up the ejector before it lands. Those ejector fragments travel for kilometers, sometimes for hundreds of kilometers, depending on the size of the impactor, and at the center of the event for a fraction of a second there is a flash. A burst of light produced by the thermal emission of vaporized rock and metal, material heated to tens of thousands of degrees, hot enough to glow brilliantly in the visible spectrum, brief enough to vanish before your brain would finish processing it if you blinked at the wrong moment. That is what Wiseman saw. That is what lit up the dark surface below Orion. Not muzzle flashes, not electrical discharge, not instrument artifacts. Rocks, arriving from interplanetary space, converting their kinetic energy into light in a fraction of a second, and then going quiet again. In 2013, Earth-based observers recorded a lunar impact flash that was visible to the naked eye for nearly a full second. That single event made international news. Follow-up imaging by the Lunar Reconnaissance Orbiter confirmed a fresh crater at the site, roughly 18 meters across, punched into the surface in an instant that most of humanity slept through. The estimated energy of that single impact was equivalent to about 5 tons of TNT, a walnut-sized rock, or maybe somewhat larger, moving at interplanetary speed, producing an explosion that would flatten a city block and shatter windows for half a mile in every direction if it had hit downtown anywhere on Earth. And critically, that was not an unusual event. It was not a rare occurrence that justified the news coverage it received. It was simply one of the ones bright enough for us to catch from 239,000 miles away through an atmosphere that was actively smearing and dimming the signal. It was the loudest voice in a crowd that had been talking the entire time. That is what the Artemis II crew was watching from orbit. Not something new, not something the moon suddenly started doing, not an anomaly triggered by a passing comet or a temporary spike in the local meteoroid environment. The same process that has been occurring every hour of every day for over 4 billion years, since the moon formed from the debris of a collision between the proto-Earth and a Mars-sized body, since it cooled from a global magma ocean into the solid airless world it is today, since life first appeared on Earth and looked up at it without the slightest understanding of what was happening on its surface. The only difference is that for one brief window on one Sunday in April, 4 human beings were in a position to actually see it happen, without the atmosphere stealing the faint ones, without the distance reducing everything to the threshold of detectability, without the sun washing out the surface in reflected glare. They saw the moon the way the moon actually is. And the moon is not quiet. It is a shooting range. It has always been a shooting range. We just kept ourselves too far away and too well cushioned to notice. And the reason we have not understood this intuitively, the reason the rate mismatch between what Artemis II observed and what our ground-based programs report felt so jarring, is that our monitoring system was never designed to see the full picture. It was designed to see what it could, from where it was, with the tools available, and for 2 decades that has been good enough to advance the science enormously. But it was never a complete census. It was always a minimum count, a lower bound, the floor of a building whose ceiling we had never measured. The ALAMO program is, by any fair assessment, an impressive piece of science. Operating since 2006 from the Marshall Space Flight Center in Huntsville, Alabama, it uses a network of small telescopes, 14-inch aperture instruments, carefully calibrated and operated by a dedicated team, to watch the moon's dark regions for transient flashes of light. The operational concept is straightforward. Point the telescopes at the unlit portion of the moon, the region in shadow that shows up as the dark limb during crescent phases. Watch, record. When something bright enough appears and disappears quickly enough, flag it as a candidate impact. Then verify, because not every flash is an impact. Cosmic ray hits on the detector, satellite reflections, instrument noise, all of these can mimic the signature of a genuine flash, and rigorous programs require multiple telescope confirmation before anything gets added to the catalogue. The ALAMO team has been extraordinarily careful. Over 2 decades, they have built the most comprehensive catalogue of confirmed lunar impact flashes in existence. About 20 detectable events per year. It is real science, rigorously conducted, and it represents a genuine contribution to our understanding of the lunar impact environment. But look at the constraints built into that number, because the constraints are where the story lives. The telescopes sit at the bottom of Earth's atmosphere. That is the first and most fundamental limitation. Every photon produced by a lunar impact flash has to make a journey of 239,000 miles through vacuum, and then, in the final 100 kilometers of that journey, pass through a turbulent, light-scattering, signal-degrading column of air before it hits the detector. Atmospheric seeing, the same optical effect that makes stars twinkle and that kept ground-based astronomy operating at a fraction of its theoretical capability before the invention of adaptive optics, smears the flash signal across a wider area on the sensor. Instead of landing cleanly on a small number of pixels with high peak brightness, the signal gets spread out, diluted, its peak intensity reduced. On a night of poor seeing, which is to say, on a typical night at any ground-based observatory anywhere on Earth, a flash that would be a clean, unambiguous signal from orbital distance becomes something closer to a soft blur, indistinguishable from the background noise that any detector accumulates over time. The atmosphere does not just add noise, it actively steals signal, and the weakest signals, the ones from the smallest impactors, the ones that are already at the edge of detectability under perfect conditions, simply vanish. They existed. They happened. The moon was struck. but the atmosphere absorbed the evidence before it could reach the detector. Then there is the timing problem, which is entirely separate from the atmosphere problem and equally constraining. You can only observe impact flashes on the portion of the moon that is in darkness. This seems obvious, but its implications are severe. The moon has to be between a waxing crescent and first quarter, or between last quarter and waning crescent, to present a large enough dark area for monitoring. During the full moon phase, there is no dark region to observe. During new moon, the moon is near the sun in the sky and essentially unobservable at night. The usable window for flash monitoring is roughly 10 to 12 nights per month, spread across 2 phase windows, and even that is optimistic. And even then, you can only observe during nighttime hours at the telescope site, which means the moon has to be above the horizon, at a reasonable elevation above the horizon, to reduce the path length through the atmosphere, and the sky has to be clear, and no other light pollution source can be interfering with the measurement. Stack all those constraints together, and the actual usable observation time, the number of hours per year when the ALAMO system is watching a meaningful dark lunar region under acceptable atmospheric conditions, shrinks dramatically. Not to 10% of the year, not to 5%, to something considerably smaller, a window that leaves the vast majority of the lunar surface during the vast majority of the hours in a year completely unwatched. So when the ALAMO program reports 20 flashes per year, it is not saying the moon gets hit 20 times per year. It is saying something far more specific and far more limited. It is saying that during the narrow windows when we can actually watch under acceptable conditions, with equipment sensitive enough to detect signals that survive a 250,000-mile journey through an obscuring atmosphere, we catch about 20 events bright enough to exceed the detection threshold. That number is the floor, the basement, the minimum possible count, the number below which the true rate cannot fall, and the gap between that floor and the actual impact rate is enormous, not twice as large, not 10 times as large, potentially orders of magnitude larger when you account for everything the ground-based system cannot see. This is the observational blind spot that Artemis II stumbled into, not by design. Nobody at NASA put "reveal the fundamental inadequacy of ground-based lunar impact monitoring in the mission objectives." The blind spot was uncovered by accident, by coincidence, by the particular geometry of one specific mission on one specific day. The solar eclipse, the proximity, the absence of atmosphere, the full darkness of the nearside surface, all converged to create conditions where the blind spot simply did not exist. For 1 hour, the filters were off. Every constraint that limits the ALAMO program, the atmosphere, the distance, the partial illumination, the restricted observation windows, all of them were simultaneously absent. And the crew saw what the moon looks like without them. 5 to 6 flashes in 60 minutes, seen from orbit, through vacuum, on a fully darkened near side lit only by faint Earthshine, with maximum contrast between flash and background, with minimum noise from any source. That is not a spike in activity. That is not the moon misbehaving. That is a glimpse through a window that is normally shuttered, bolted and plastered over, a window that the entire history of human lunar observation had never once managed to open. And the view through it is not alarming because it is new. It is alarming because it is accurate, because it shows you the thing you were always looking at, finally without the veil. And the reason this matters, the reason this is not just an interesting footnote in a mission report to be filed away and occasionally cited in academic papers, is that we are planning to send people to live on that surface, permanently, not for a long weekend, not for a week, for months, for years. Eventually, if the vision holds, for the rest of their lives, in habitats that will sit exposed to the same bombardment the Artemis II crew watched from the safety of orbit, protected by nothing but the engineering solutions we design based on our understanding of the impact environment. And if that understanding has a blind spot at its centre, if our best impact rate estimates are built on a detection flaw rather than a true count, then the engineering solutions are being calibrated against an incomplete picture of the threat they are meant to address. The question is no longer whether the moon gets hit. Every planetary scientist alive has known the answer to that question for decades. The question is how much of the hitting we have been missing. How wide is the gap between what ALAMO records and what is actually happening? How much of the flux distribution lives below the ground-based detection threshold? How many events in the size range that matters most for habitat engineering, not the city-leveling impacts that would be unambiguously catastrophic, but the intermediate events that could punch through a pressure wall without warning, are occurring at rates we have never directly measured? And the answer, based on everything we know about meteoroid flux models, about the physics of the size distribution, about the detection limits of every instrument we have ever pointed at the moon, is most of it. Most of what is happening on the lunar surface, most of the impacts, most of the flashes, most of the energy deposition, is invisible to us from where we stand. We have been watching the moon for 400 years with increasingly sophisticated instruments, and we have been seeing a fraction of a fraction of a fraction of its reality. The Artemis II crew, for 1 hour, saw more. Not everything, but more. And more was enough to make it clear that our picture of the moon, the quiet moon, the postcard moon, the museum exhibit moon that stopped changing long ago, was never the moon at all. It was the limit of our instruments, projected onto the sky and mistaken for truth. Part 3. The numbers that break intuition. Let me give you 2 numbers, and then let me explain why putting them next to each other is both misleading and essential. Number 1. NASA's ground-based monitoring averages roughly 20 confirmed lunar impact flashes per year. Number 2. The Artemis II crew observed 5 to 6 impact flashes in approximately 1 hour. If you do the naive math, if you just scale that hourly rate up to a full year, you get something like 43,000 to 52,000 flashes per year. That is over 2,000 times the ground-based detection rate, and that number is wrong. It is almost certainly an overestimate, possibly a dramatic one. But the reason it is wrong is more important than the number itself, because understanding why it is wrong teaches you more about the moon than the correct number ever could. And understanding why it is wrong also teaches you something uncomfortable about how science works, about how our tools shape our perception, and about how confidently we can describe a world we have only ever seen through a keyhole. The crew's 1-hour observation was not a random sample of average conditions. It was a directed sample of ideal conditions, maximum contrast between flash and background, no atmosphere between the observer and the surface, close range, a few thousand miles rather than 250,000, full surface darkness produced by a total solar eclipse geometry that no human observer had ever occupied before. If you sat down with a blank piece of paper and tried to design the perfect observational scenario for detecting the faintest possible impact flashes on the lunar surface, you would design almost exactly what Artemis II experienced by accident. Every variable that normally degrades the signal was simultaneously absent. Every factor that normally inflates the noise floor was removed. The crew was not observing the moon under typical conditions and seeing an unusually high rate. They were observing the moon under uniquely perfect conditions and seeing the rate that was always there. The detection rate during that window was almost certainly higher than what you would measure if you could somehow watch the moon continuously from the same orbital distance under average lighting conditions, because the eclipse geometry allowed them to see flashes far fainter than what any standard observation, even from orbit, would normally catch. They were sampling deeper into the size distribution than any instrument we have ever pointed at the moon could reach. But here is the thing. Even if you discount the Artemis observation rate heavily, even if you assume that half of what they saw was enhanced by those exceptional conditions, or that the timing coincided with a minor meteoroid stream that temporarily elevated the flux above its long-term average, you still end up with a detection rate that is orders of magnitude above 20 per year. Not twice as high, not 10 times as high, orders of magnitude. And that is not a surprise to the planetary scientists who study this environment for a living. The models have been saying this for decades. The theoretical predictions, built on orbital particle detector data and crater size frequency distributions and calculations of the interplanetary dust complex, have long pointed toward a true impact rate far higher than any ground-based detection program could ever confirm. We just have not had the visual confirmation from human observers, the visceral, undeniable, I watched it happen with my own eyes confirmation, to make it feel real in the way that numbers on a page never quite do. So let us talk about the numbers on the page, because they are worth understanding properly. The meteoroid environment around the Moon is not a mystery. It is not an open scientific question in the sense that researchers are confused or uncertain about the basic parameters. It has been studied extensively through multiple independent lines of evidence. Orbital particle detectors aboard spacecraft like the Lunar Atmosphere and Dust Environment Explorer, known as LADEE, have directly sampled the population of particles in cislunar space and measured their mass, velocity and flux. Crater counting on returned lunar samples, rocks brought back by Apollo astronauts that have been sitting on laboratory shelves for over 50 years, reveals the accumulated micrometeoroid bombardment history written into the surfaces of those rocks at the microscopic level. Surface exposure analysis uses the distribution of cosmogenic isotopes, atoms created by cosmic ray bombardment in the absence of any atmospheric shielding, to reconstruct how long surfaces have been exposed and at what rate material has been deposited on them. Theoretical modelling of the interplanetary dust complex, the vast cloud of debris that fills the inner solar system, produced by comets shedding material as they approach the Sun and asteroids grinding against each other in the belt, provides a framework that ties all of these observational threads together. The consensus picture that emerges from all of this work is well established, and once you sit with it for a moment, genuinely difficult to fully absorb. Roughly 1.4 metric tons of meteoroid material strikes the lunar surface every single day. That is not a typo, not a misplaced decimal point. 1.4 metric tons every 24 hours, 365 days a year, through every season and every phase cycle, regardless of whether anyone is watching. Over the course of a year, that adds up to more than 500 metric tons of extraterrestrial material raining onto a world with no defense mechanism whatsoever. No atmosphere to burn it up, no magnetic field to deflect the charged component, no weather to erode the craters it leaves behind. Every gram of it arrives, deposits its energy, and becomes part of the Moon forever. 500 tons a year, accumulated over 4.5 billion years. That is the archive you're looking at when you look at the lunar surface, a continuous record of everything the solar system has thrown at it, written in rock, preserved perfectly in an environment where nothing erases anything. Now the overwhelming majority of that daily 1.4 tons comes in the form of particles you would never see, even if you were standing on the surface watching. Dust grains, microscopic fragments, particles smaller than a grain of sand, often smaller than a human hair, moving at the same hypervelocity speeds as the larger impactors, but carrying so little total energy that their individual impacts produce no visible flash, no detectable seismic signal, no crater you could photograph from orbit. They are too small to produce an optical signature visible to any camera we have ever built, but they are not too small to matter. They erode surfaces, they pit glass, they implant atoms into the uppermost atomic layers of whatever material they strike. They sputter material off exposed surfaces, gradually grinding down rocks and coatings and structural elements at a rate that becomes significant over the timescales of a long-duration mission. They are individually invisible and collectively relentless, and they represent the vast majority of the mass flux that the Moon absorbs every day. The size distribution of impactors follows what mathematicians call a steep power law. The relationship between size and frequency is not linear. It is not even gently curved. It is steep, dramatically steep, meaning that for every object large enough to produce a flash visible from Earth, there are thousands of objects in the next smaller size class, and millions in the size class below that, and billions below that. The population explodes exponentially as you move down the size scale. The visible flashes, the events that the Artemis crew witnessed, and that the Alamo telescopes occasionally catch from Earth, represent the high-energy tail of this distribution, the rare big ones, the impactors that release enough energy in a bright enough burst to produce an optical signature that can survive the journey to a detector. They are real, they are dramatic, but they are not the story. The story is the invisible population beneath them, the part of the distribution that does not produce visible flashes, but that is striking the surface at a rate that dwarfs anything the telescopes record. And this is where the ground-based detection rate of 20 per year becomes so deeply misleading if you take it at face value. 20 per year does not mean the Moon experiences 20 impacts per year. It does not even approximately mean that. It means that out of the continuous, relentless hail of material striking the surface every second of every hour of every day, we can only detect the very brightest events, and only during the narrow windows when our instruments happen to be watching under acceptable atmospheric conditions. The actual number of impacts producing visible flashes, if you could watch the entire lunar surface continuously from orbital distance with no atmospheric interference between you and the surface, is estimated to be somewhere in the range of several thousand per year for events that exceed the ground-based detection threshold. Several thousand, not 20. And below that threshold, where the ground-based systems simply cannot reach, the numbers climb exponentially, consistent with the steep power law that governs the size distribution. The flash you can see from a telescope in Alabama is not a typical event. It is an outlier. The typical event is invisible to everything we have built so far. What the Artemis crew did, by accident, without intending it, was lower the detection threshold. Dramatically. By being closer to the surface. By having no atmosphere absorbing and scattering the signal. By observing during the perfect darkness created by the eclipse geometry. They could see flashes that no Earth-based system will ever record. Flashes from impacts too small and too faint to register on any ground-based detector, no matter how large or how sensitive. They were reaching down into the size distribution to a depth that had never been accessed by human observation before. And the rate they observed, 5 to 6 events per hour, is entirely consistent with the rate predicted by the flux models for a lower detection threshold applied to a fully dark lunar hemisphere observed from close orbital range. It is not an anomaly. It is not evidence that something unusual happened on April 6th. It is the model, confirmed visually for the first time in history. The theory predicted this. The observations matched. The gap was not between prediction and reality. The gap was between reality and what we could see from Earth. This is the central realization of everything the Artemis II mission revealed about the lunar environment, and I need you to hold on to it firmly because everything that follows builds from here. The Moon did not get more dangerous on April 6, 2026. Our measurement got more accurate. Artemis II did not discover new impacts. It discovered old blind spots. The bombardment has been happening at this rate, and almost certainly at rates far higher in the deeper size distribution, for the entire history of the solar system. We could not see it from where we were standing. Now, for one brief hour, we had someone standing somewhere else, and the view was clarifying in a way that nothing we have built on the ground has ever managed to be. Let me push this further, because the flux picture is not just about total rates. It has structure, it has geography. The meteoroid environment around the Moon is not uniform across the surface, and the non-uniformity matters enormously for where we plan to go. The flux varies with geometry in ways that have been measured and modelled extensively. One of the most important variations is the asymmetry between the Moon's leading hemisphere and its trailing hemisphere. As the Moon orbits Earth, and the Earth-Moon system orbits the Sun, the Moon effectively moves through the interplanetary particle environment the way a car moves through rain. The front of the car gets wetter than the back. The hemisphere facing into the direction of orbital motion sweeps up more particles than the hemisphere trailing behind. For the Moon, this creates a measurable difference in impact rates between the two sides, with the leading hemisphere experiencing higher flux than the trailing hemisphere. The sub-Earth point, the region of the near side that faces most directly into the Earth-Moon system's orbital path at certain times of year, experiences a flux roughly 1.6 times higher than the anti-Earth point. This asymmetry is not subtle. It is a 60% difference in impact rates between different parts of the same world, and it has been confirmed by crater density measurements from orbital imagery. More craters on the leading side, fewer on the trailing side. The bombardment is real, it is measurable, and it has a direction. There is also temporal variation. The Moon regularly passes through meteoroid streams, ribbons of debris shed by comets over thousands of years that spread out along the comet's orbital path and intersect the Moon's orbit at predictable times each year. When the Moon passes through a dense part of one of these streams, the impact rate spikes temporarily above the long-term average. Earth experiences this same phenomenon as annual meteor showers, the Perseids in August, the Leonids in November, the Geminids in December. The Moon experiences analogous events, without the atmosphere to burn up the incoming particles, without the sky show that makes the Earth-based version so memorable. Some analysts reviewing the Artemis II observation data noted that the apparent clustering of the observed flashes in space and time might suggest the Moon was passing through a minor stream during that window, which could have contributed to the elevated rate. That is plausible. It is even likely. But it does not diminish the significance of the observation, because even if a stream contributed to what the crew saw, the stream itself is part of the normal lunar impact environment. Streams are not extraordinary events. They are a recurring feature of the bombardment the Moon experiences every year. The Artemis crew did not happen to catch a once-in-a-century spike. They happened to be in the right place at the right time to see what the Moon deals with regularly. And now I need to tell you about one specific flash from the crew's report, because its location carries weight that goes far beyond its individual energy. At least one of the observed impacts occurred near the lunar South Pole. That sentence, placed in context, is not a scientific footnote. It is a direct challenge to a set of assumptions that are currently driving billions of dollars of mission planning and infrastructure investment. The lunar South Pole is the region where NASA, ESA, JAXA, and multiple international partners plan to establish the first long-duration human presence beyond low Earth orbit. Artemis III, the first crewed lunar landing of the post-Apollo era, is designed to put astronauts down near the South Pole. The proposed Lunar Gateway orbital station will support surface operations in the polar region. The long-term vision, the one that fills the planning documents and the budget justifications and the international partnership agreements, includes permanent habitats, resource extraction facilities for mining water ice and producing propellant, and scientific outposts. All of it clustered at the pole, all of it built on the assumption that the pole is the best place to build, and by most engineering assessments, that assumption is correct. The advantages are real, and they are substantial. Certain crater rims near the South Pole are in near-constant sunlight, providing almost uninterrupted solar power in a region where equatorial sites swing between 2 weeks of blazing daylight and 2 weeks of brutal darkness. Permanently shadowed craters at the bottom of the same poles trap water ice, delivered over billions of years by comet and asteroid impacts, that can be mined and electrolyzed into hydrogen and oxygen for fuel and life support. Thermal environments near the poles are more stable than the equatorial zones, where surface temperatures swing from above 100 degrees Celsius in sunlight to below negative 150 in shadow within the space of a few meters. The South Pole, by any rational engineering analysis, is the best real estate on the Moon. But best does not mean safe. And watching an impact flash occur near the coordinates where human beings plan to build their first permanent off-Earth home adds a layer of reality that no model or statistical table ever quite manages to deliver. One flash, near the South Pole seen by human eyes from orbit. That single event is not statistically significant. You cannot derive a population-level impact rate from one observation. The error bars are enormous. But the psychological weight of it is real, and it is legitimate, because it is a reminder, delivered in the most visceral way possible, that the place we have chosen to call home is under constant fire. Not metaphorically, not statistically, literally. Rocks are hitting it while we plan construction schedules. The flux model suggests the polar regions may actually experience slightly lower impact rates than the equatorial zones for certain meteoroid populations. The geometry of polar latitudes, the way impactors approach at shallower angles combined with the specific velocity distributions of the dominant particle populations, produces a modestly reduced flux compared to the equatorial belt. But slightly lower is a relative term that requires context to mean anything. Slightly lower than constant bombardment is still bombardment. Slightly lower than several thousand detectable flashes per year across the surface is still several hundred in the polar region. Slightly lower than 23,000 micrometeoroid strikes per year on a habitat-sized structure is still a number that demands serious engineering attention. The models do not give the South Pole a pass, they give it a modest discount. And a modest discount on the price of living under a continuous meteoroid bombardment is still a very high price. We have been designing lunar habitats based on what we could see from Earth. And what we could see from Earth was a fraction of what is actually happening. The Artemis II observation did not change the physics of the impact environment. The physics were never in question. What it changed was the calibration. It provided a direct visual data point from inside the cislunar environment that can be used to validate or challenge the flux models in a way that ground-based observation never could. If the models are already correctly accounting for flux rates well above the ground-based detection numbers, then the engineering designs being developed for lunar habitats are probably aimed at the right target. But if the models have their own blind spots, if there are aspects of the flux environment at low energies, at certain approach angles, at specific temporal scales that have not been fully captured by the orbital detectors and the crater counts and the theoretical frameworks, then the safety margins being built into the designs may be thinner than the planners believe. That is not a reason to cancel the program. It is not a reason to walk back the commitments to return humans to the moon. It is a reason, a compelling and urgent reason, to take the data from Artemis II seriously, to fund dedicated orbital impact monitoring systems that can do continuously what the Artemis crew did accidentally for 1 hour, to update the flux models with direct observational data gathered from cislunar space rather than inferred from Earth, to make sure that when we commit human lives to permanent lunar habitation, we are doing so based on a complete picture of the environment, rather than the best picture we could construct from 239,000 miles away through 100 kilometers of atmosphere that was hiding most of what we needed to see. Because the gap between what we thought we knew and what the Artemis II crew actually saw is not a gap in lunar activity. The moon was always doing this. The gap is in human perception. It is a gap created by our location, our instruments, our atmosphere, and 400 years of watching the moon from the wrong place and calling the view complete. That gap is the single most important thing this mission revealed, and closing it is the single most important thing the next generation of lunar science needs to accomplish. Part 4. Building a home in a crosshair. So now you know the moon gets hit constantly. You know the rate is far higher than our ground-based numbers suggested. You know the Artemis II crew saw it happen in real time, from a vantage point that stripped away every observational filter we normally depend on. The question that follows is the obvious one. We still want to build there. We still want to send people to live on that surface for months, then years, then permanently. What does constant bombardment actually mean for a habitat? The answer connects directly to what the Artemis crew witnessed, because the same blind spot that hid the true impact rate from our telescopes threatens to hide the true engineering risk from our mission planners. If we undercount the impacts, we underestimate the threat, and if we underestimate the threat, we underdesign the protection. This is not an abstract concern about modelling accuracy. It is a concrete concern about whether the structures we are planning to send human beings into will keep those human beings alive. The proposed Artemis surface habitats are not like the International Space Station, and that distinction matters enormously. The ISS orbits in low Earth orbit, roughly 400 kilometers up, protected to a significant degree by Earth's magnetic field, and, for debris in certain orbits, by atmospheric drag that gradually clears the orbital environment of smaller particles. The station also benefits from something that is easy to overlook: proximity. If a critical system fails on the ISS, the crew can be in a Soyuz or Crew Dragon and headed home within hours. There are contingency plans for contingency plans. The entire architecture of human spaceflight in low Earth orbit is built around the assumption that Earth is close, that rescue is possible, that the margin for error, while thin, exists. A lunar surface habitat has none of those advantages. No magnetic field, no atmosphere, no quick ride home. The Moon sits in the same interplanetary meteoroid environment as every other airless body in the inner solar system, completely unshielded by any planetary magnetosphere. If a micrometeoroid punctures a pressure vessel wall on the Moon, the crew is dealing with a depressurization event on a world where the nearest help is 250,000 miles away and 3 days of travel time under the best possible circumstances. There is no emergency extraction. There is no rescue shuttle on standby. The habitat either protects the people inside it, or those people die. That is the operational reality that every engineering decision about lunar habitation has to reckon with. The long-duration exposure problem is what makes this fundamentally different from Apollo. It is tempting to reason from Apollo, because Apollo is the only precedent we have for humans on the lunar surface, and Apollo went fine. But Apollo's surface stays were brief, almost beyond belief by the standards of what Artemis and its successors are planning. The longest Apollo surface stay was Apollo 17, which spent just over 74 hours on the Moon. Not 3 days of actual exploration time, but 74 hours total, from landing to liftoff. Artemis III aims for roughly a week. Future missions under the Artemis architecture will extend to weeks, then months. The planned lunar gateway and surface outpost envision permanent or semi-permanent occupation, potentially spanning decades. Each step in that progression multiplies the exposure time, and with it, the cumulative probability of something going wrong. Think of it in simple probabilistic terms. If the chance of a significant micrometeoroid impact causing a critical failure on any given day is very small, that small daily probability compounds across years into something that can no longer be dismissed. A 1 in 10,000 daily chance of catastrophic breach sounds vanishingly unlikely. Across a 20-year mission, it represents a near certainty of at least one such event occurring. This is the arithmetic of long-duration exposure, and it is the arithmetic that Apollo's brief visits never had to confront. Every additional hour on the surface is another hour of exposure to the same bombardment that lit up the Artemis II crew's observation window in real time. The flashes the crew saw, the 5 or 6 visible events during their transit, were the large ones, the bright ones. The impactors big enough to produce an optical signature visible from thousands of miles away, objects capable of excavating craters meters wide in a fraction of a second. Those events are dramatic. They are the ones that make footage and generate headlines. But in terms of the actual engineering threat to a habitat, they represent only the thinnest sliver of the total flux. They are statistical outliers on the large end of a size distribution that extends downward through many orders of magnitude. Beneath them, in that size distribution, there is a population of particles so numerous and so small that they are individually invisible but collectively relentless. These are the micrometeoroids, particles typically smaller than a millimeter across, sometimes smaller than 100 microns, which is thinner than a human hair. They move at the same hypervelocity speeds as their larger cousins, anywhere from 10 to 70 kilometers per second depending on their orbital origin, because speed in the interplanetary environment is governed by orbital mechanics, not by size. A particle the width of a dust grain travelling at 20 kilometers per second carries kinetic energy wildly disproportionate to its mass, and a recent study estimates that a lunar surface structure with an exposed area comparable to the International Space Station would be struck by between 15,000 and 23,000 of these particles every single year. Pause on that number, 23,000 impacts per year, on a single structure. That is not a dramatic one-time event to plan around and then move on from. That is continuous erosion. It is a slow, invisible sandblasting that never stops, that operates at every scale simultaneously, that degrades surfaces, pits optical coatings, weakens structural materials, and accumulates damage over time in ways that are easy to ignore in the short term and catastrophic in the long term. This is the deep connection to what Artemis II revealed. The visible flashes were the tip of an iceberg. The unseen micrometeoroid flux is the immense mass beneath the waterline, invisible, unspectacular, and far more threatening over mission timescales than any single large impact event. Just as our ground-based telescopes could only see the brightest impacts and missed the overwhelming majority of smaller ones, our engineering intuition naturally focuses on the dramatic single-event failures while underweighting the slow, steady degradation that is actually more dangerous when you're planning to live somewhere for decades. Every one of those 23,000 annual micrometeoroid impacts is a tiny experiment in material failure. Each one excavates a microscopic crater in whatever surface it strikes. Glass, metal, composite, polymer, thermal fabric. It does not matter what the material is. The particle arrives faster than sound, travels through any solid material, which means the surface it hits has no time to respond elastically, no time to flex or absorb. The impact site becomes a miniature version of the same plasma and shockwave event that produces visible flashes from larger impactors. A jet of vaporized material ejects from the crater at high velocity. A hemispherical shockwave propagates into the surrounding material, producing subsurface cracking that extends well beyond the visible crater rim. The particle itself may be completely vaporized, but the damage it leaves behind is real, permanent, and structural. Over years, the cumulative effect of tens of thousands of these events is like sandpaper, applied by a machine that never turns off and never dulls. Thermal blankets, which insulate habitats against the extreme temperature swings of the lunar surface, swings from over 100 degrees Celsius in sunlight to negative 170 in shadow, degrade as their reflective layers are peppered with microscopic holes. Solar panel surfaces cloud as their cover glass accumulates pitting that scatters incoming light and reduces power output. Structural joints accumulate stress microfractures that individually mean nothing but collectively reduce the margin against fatigue failure. Seals, gaskets, and pressure fittings weaken as their surfaces are abraded at the molecular level. And because each individual impact is far too small to trigger any sensor or alarm, the damage accumulates silently, invisibly, until some threshold is crossed and something fails, often without warning, often in a way that is difficult to diagnose and harder to repair. This is not speculation drawn from models alone. We have direct physical evidence from decades of operating hardware in space. After decades in low Earth orbit, the exterior surfaces of ISS modules show thousands of micrometeoroid and orbital debris impact craters visible to the naked eye during spacewalks. Some of those craters are large enough to be genuinely alarming. A centimetre-wide divot in a module wall is not a comfortable thing to contemplate. Cupola windows on the station have been damaged by impacts from particles estimated to be only a few thousandths of a millimetre across, producing visible chips and pitting that necessitated monitoring and, in some cases, precautionary replacement. Handrails used by spacewalking astronauts show erosion patterns consistent with years of hypervelocity particle exposure. The radiator panels that reject waste heat from the station systems are riddled with impact sites. This is what long-duration exposure to the space environment looks like in practice, and that is on a platform that, as noted, has it comparatively easy. The ISS benefits from Earth's magnetic field, which deflects a significant fraction of the charged particle flux that would otherwise add to the erosion burden. It operates in low Earth orbit where the meteoroid flux, while still present, is lower than in the interplanetary environment the Moon inhabits. And yet, even with those advantages, the cumulative damage after 2.5 decades of continuous operation is extensive and well documented. On the Moon, there is no magnetic field assistance. The meteoroid flux is higher. The exposure is continuous and unrelenting. The cumulative damage rate over equivalent time periods would be correspondingly and substantially worse. What Artemis II showed us visually, the Moon getting hit over and over again in real time, flashes of light appearing and disappearing across the surface, is the large-scale, optically visible version of what a habitat's walls would experience invisibly, constantly, and at a microscopic level for as long as they stand. The engineering response to this threat is not nothing, and it would be unfair to the engineers and material scientists who have spent decades developing it to suggest otherwise. The standard approach to micrometeoroid protection in spacecraft design is the Whipple shield, named after the astronomer Fred Whipple, who first proposed the underlying concept in the 1940s, long before it became a practical necessity. The idea is conceptually elegant and physically sound. Rather than building a single thick wall and trying to make it strong enough to stop incoming particles directly, you build two or more thin walls separated by a gap. When a hypervelocity particle strikes the outer bumper wall, it punches through. The bumper is not designed to stop it. But in punching through, the particle and the wall material both shatter and vaporize, converting the single concentrated projectile into an expanding cloud of smaller, slower, more diffuse debris. That debris cloud spreads across the gap between the walls. By the time it reaches the inner pressure wall, the energy that was concentrated in one particle moving at tens of kilometers per second has been distributed across a much wider area, moving at a lower effective velocity, and the inner wall can absorb it without being penetrated. Modern Whipple shields have evolved considerably from Whipple's original two-wall concept. Contemporary designs use multiple intermediate layers of specialized materials, ceramic fabrics like Nextel, metallic meshes, combinations of high-strength polymer films, each serving a specific function in the progressive disruption and energy distribution sequence. The performance of these systems is impressive. Well-designed modern Whipple shield configurations can intercept an estimated 99.9997% of incoming particles at design velocities and angles. Stated that way, the protection sounds nearly absolute. But nearly absolute is not absolute, and the mathematics of long-duration exposure are unforgiving. The remaining 0.0003% of particles applied to 23,000 impacts per year still means that roughly one particle in every 3 million gets through. Over 10 years, that represents a statistically meaningful number of penetration events. Over 20 years, the probability of at least one significant breach, one event in which a particle penetrating the inner wall causes a detectable pressure loss, is not negligible. It is in fact a design parameter that has to be actively managed through redundant pressure vessels, rapid leak detection systems, and protocols for emergency patching that can be executed by crew members in spacesuits while exposed to the same environment that caused the problem in the first place. Whipple shields also have scaling limits that become increasingly problematic as habitat ambitions grow. They work well for the relatively compact, well-defined module geometries that characterize current spacecraft design. But as habitats expand to support larger crews, more equipment, longer missions, and eventually permanent occupation, the total exposed surface area grows. A habitat complex designed to house a crew of 12 with full life support redundancy, manufacturing capability, and scientific laboratories might have 10 or 20 times the exterior surface area of a single ISS module. That means 10 or 20 times the annual impact count, which means 10 or 20 times the Whipple shield area to maintain, inspect, and eventually repair or replace. The mass penalty for shielding large structures to the same protective standard as small ones scales badly, adding launch mass, increasing structural loads, complicating construction sequences, and raising costs in ways that become prohibitive at the scales envisioned for permanent lunar settlement. And this is before accounting for the possibility that the true micrometeoroid flux is higher than current models suggest. The Artemis II observation revealed a significant undercounting of large impact events compared to ground-based predictions. If that same observational blind spot, the same systematic underestimation arising from the limitations of Earth-based monitoring, extends even partially into the micrometeoroid size range, then the impact rates that current shielding designs are calibrated against may be optimistic. The margins built into those designs may be thinner than the engineers who built them believe. Getting the flux numbers right is not an academic exercise. It is the foundation on which every shielding decision rests. This is why many lunar habitat designers, thinking seriously about permanent occupation rather than extended visits, have concluded that the only engineering solution with genuine long-term viability is not a shield you design in a laboratory and carry to the moon. It is a shield the moon already provides for free in effectively unlimited quantities. Regolith, the loose, fragmented, pulverized rock and dust that blankets the lunar surface to depths of several meters, the product of billions of years of the same bombardment we are now worrying about, is an extraordinarily effective absorber of kinetic energy. Put 2 to 3 meters of regolith on top of a habitat structure, and you have a shielding layer whose aerial density no manufactured material can match at any reasonable cost or launch mass. A particle that would punch straight through a Whipple shield at high speed encounters meters of granular material that progressively absorb, scatter, and ultimately stop it entirely long before it reaches any pressurized wall. The regolith approach has a second major benefit that compounds its attractiveness. Cosmic radiation, the high-energy particles that stream continuously through the interplanetary environment, originating from both the Sun and galactic sources, poses a serious long-term health risk to anyone living on the lunar surface for extended periods. Unlike micrometeoroid impacts, radiation exposure has no catastrophic single-event failure mode. It accumulates, slowly increasing cancer risk, degrading the immune system, affecting the central nervous system in ways that are still being characterized. Shielding against cosmic radiation requires mass, lots of it, placed between the crew and the sky. A 2 to 3 meter regolith overburden that stops micrometeoroids also provides substantial radiation shielding, addressing 2 of the most serious long-duration hazards with a single architectural decision. The excavation and construction challenges this approach entails are, to put it plainly, enormous. Moving the hundreds or thousands of tons of regolith required to cover a habitat of meaningful size requires heavy equipment, excavators, haulers, graders, that does not currently exist in flight-qualified form, has never been tested in the lunar environment, and would itself need to be landed on the moon before any construction could begin. Building pressure-sealed structures with sufficient structural integrity to bear the weight of a continuous regolith overburden, without settling, cracking, or deforming over decades, requires structural engineering approaches well beyond anything currently in the habitat prototype pipeline. The construction sequence, in which workers in spacesuits on an airless world must assemble large pressurized structures and then bury them under meters of loose fragmented rock, is operationally complex in ways that make the construction of the ISS look straightforward by comparison. The entire regolith shielding approach depends on in-situ resource utilization at a scale that has never been demonstrated anywhere but laboratory. Moving and placing regolith by the 1,000-ton requires not just the equipment, but the power to run it, the communications infrastructure to supervise it, the maintenance supply chain to keep it running when it inevitably breaks, and the human expertise on site to make decisions when the plan meets reality. The habitat essentially becomes an underground installation, which transforms every subsequent design question. How do you provide natural light to inhabitants of a bunker? How do you ventilate it, expand it, maintain its exterior, conduct emergency egress? The underground architecture that solves the shielding problem creates an entirely new class of problems for habitability, human factors, and psychological well-being over long tours of duty. None of these challenges are insurmountable. Human beings have built underground structures in difficult environments throughout history, and the engineering problems of lunar habitat construction, while genuinely hard, are problems of engineering rather than fundamental physics. They can be solved, given sufficient resources, sufficient time, and crucially, sufficient understanding of what the environment actually demands. That last requirement is where the Artemis II observation becomes most consequential. The physics of the lunar environment are not negotiable. The moon is under constant bombardment. The Artemis II crew saw the bright, visible end of that bombardment directly with their own eyes. The models, now being revised upward in light of what they observed, tell us the invisible end is thousands of times more frequent. And the only way to build a permanent human presence in that environment is to acknowledge the bombardment not as a contingency to plan around, but as a baseline condition to design for, the default state of the world where we intend to live. The blind spot that hid the true impact rate from our telescopes is the same blind spot that risks hiding the true engineering challenge from our planners. Both involve looking at an overwhelming phenomenon through an instrument too limited to capture its full scale, and concluding, from incomplete evidence, that the situation is more manageable than it actually is. What Artemis II did, by accident, by the simple act of placing human observers in a position where no instrument limitation could filter what they were seeing, was pull back the curtain on one. The implicit warning about the other is there for anyone willing to follow the logic where it leads. Part 5. The silence after the flash. There is a strange symmetry to the moon's surface that becomes impossible to ignore once you have watched it get hit. Every crater you can see, from the giant basins visible to the naked eye down to the microscopic pits that cover every rock and every grain of regolith, every single one of those marks is an impart. The moon has no volcanoes reshaping its face, not anymore. No rivers eroding its plains. No wind smoothing its ridges. No tectonic plates recycling its crust. What hits the moon stays on the moon, forever, or at least for the billions of years until the next larger impart erases the previous one. The surface is a record, an unbroken archive of collisions stretching back to the formation of the solar system, written in a language of craters that never gets edited, never gets revised, never gets erased by weather or time. What the Artemis II crew saw was not a new chapter. It was the current page being written in real time, the same process that created every feature they could see below them, still partive, still ongoing, still adding to the record one flash at a time. And that is what made the observation so powerful, not as science, but as experience. For decades we have understood the lunar impart environment through numbers, flux rates, size distributions, probability curves, energy estimates. These are abstractions. They live in papers and databases and engineering specifications. They are processed by computers and summarized in briefings and filed in mission planning documents. They are true. They are accurate. They are also, in a very human sense, not real, not until someone sees it. The Artemis II crew crossed that line. They took a statistical abstraction and turned it into a lived moment. Wiseman did not report a data point. He reported a flash. Something he saw with his eyes, something that produced an involuntary emotional response, something that briefly made the moon stop being a destination on a planning chart and start being a place where things explode. That transition, from model to witness, is not scientifically important. The physics do not care whether a human was watching, but it is humanly important because it is the kind of experience that rewires priorities. The crew's repulsions tell the story. Giddy. That was one of the words used. Not afraid, not alarmed, giddy. There is a particular kind of joy that comes from seeing something you were not prepared for, something that reframes your understanding in real time, and the Artemis II crew clearly experienced it. The Earthshine was serene. The corona was magnificent, and the surface was exploding, all at once, beauty and violence occupying the same frame, inseparable, simultaneous. That cognitive dissonance, that inability to reconcile the peaceful appearance of the moon with the energetic reality of its environment, is not a failure of perception. It is the most honest possible response to a world that has been fooling us with its stillness for as long as we have looked at it. And that brings us to the question that has been building beneath every F-part and figure in this story. Can we partially live there? Not visit, not plant a flag and leave. Live, build habitats, raise structures, maintain systems, grow food under artificial light inside pressure vessels buried under 3 meters of regolith on a world that gets hit by over a ton of space debris every single day. The engineering is theoretically possible. The shielding concepts work in simulation. The regolith burial approach provides adequate protection on paper. The risk models, when you run them out to 10, 20, 50 years of continuous occupation, produce numbers that are within the range of what human institutions have historically accepted for frontier environments. But all of those models are built on inputs. And the single most important input, the meteoroid flux, is the one that Artemis II just told us we have been underestimating. Not because the models are wrong. The models are sophisticated and well calibrated. But because the observational data feeding those models comes from the same Earth-based systems that could only see a fair portion of what was happening. The crew saw what the telescopes missed. And if there are similar blind spots in other size ranges, other velocity ranges, other temporal patterns that our sampling has not captured, then the confidence intervals around those engineering calculations may be wider than we think. This is not a reason to abandon the moon. It is a reason to go back with better instruments, to deploy orbital monitoring systems that can watch the surface continuously from close range, to build dedicated IMPART flash observatories in lunar orbit that do what the Artemis II crew did by accident, on purpose, all the time, to replace our Earth-centric view of the lunar environment with a lunar-centric one, because the gap Artemis II revealed was not a gap in knowledge, it was a gap in perspective. We were looking at the moon from the wrong place and calling what we saw the whole picture. The moon did not change on April 6, 2026. It did expertly what it has been doing for 4.5 billion years. It sat there, airless and unshielded, and absorbed everything the solar system threw at it. Rocks, dust, fragments of comets and asteroids, and the scattered debris of planetary formation. It took every hit and recorded every one, silently, permanently, without complaint. The only thing that changed was us. We finally put someone close enough, in the right geometry, at the right moment, to see what was always happening. And what they saw was this. The moon is not quiet. It has never been quiet. It is a world under continuous bombardment, absorbing imparts at every scale, from microscopic dust grains to rocks the size of your fist, every hour of every day. We did not know that, not viscerally, not experientially, because we were watching from too far away, through too much atmosphere during too few hours. Our picture of the moon was shaped by our limitations, not by the moon's reality. That is the real lesson of Artemis II. Not that the moon is more dangerous than we thought, but that we have been seeing less of it than we assumed. The danger was always there. The flashes were always happening. We just were not in position to notice. And now that we have noticed, the question is simple. We know what the moon partially is. We have seen it with human eyes, unfiltered from orbit. A place of continuous silent violence, beautiful and indifferent, utterly unconcerned with whether we build there or not. Do we still want to go?